Hi, this video is about understanding that double precision floating point types are not perfectly precise. The goal is to understand the precision limitations of binary floating point types like doubles, to highlight some of the pitfalls you could face if you're not aware of this imprecision, and give some basic suggestions on making designs more robust to these imprecisions. So first off, doubles are an amazingly successful data type for high precision scientific and engineering calculations. Doubles are the default for many languages, including MATLAB, Simulink, C++, and so forth. Since the 1980s, it's been nearly impossible to buy a personal computer that doesn't have hardware acceleration for floating point math, including doubles. Doubles have an incredible range from roughly 10 to the minus 300 up to 10 to the plus 300. They also have an incredible representational precision that's normally better than 1 part in 9,000 trillion. But doubles are not perfectly precise for all values. That fact often surprises people. This leads to wasted time, and it can also lead to bad designs that have negative impact. So this presentation explains why doubles can have imprecision for certain values and gives some design advice for handling that. First, let's do a refresher on integers and factors. All integers can be represented as a product of prime factors. For example, 20 could be factored into 2 times 2 times 5. Those are its prime factors. Given two integers a and b, then a equals b if and only if the factors of a equal the factors of b. Now let's apply that to this sort of mini quiz. So the question is, does there exist positive integers q and n such that 5 divided by 100 exactly equals the integer n divided by 2 to the integer exponent q? So let's take the left-hand side and take the integer in the denominator and factor that. So 100 factors into 5 squared times 2 squared. Okay? We can then cancel out the 5's to simplify the terms on the left-hand side. Next, we can turn this rational equation into an integer equation just by multiplying both sides by both denominators. And now we look at this integer equation. The integer on the left is obviously, its factors are multiple powers of 2. But on the right-hand side, we see a 5. It doesn't matter what the rest of it is. It doesn't matter that we don't know what the integer n is. We see a 5, therefore the factors on the right side have a 5 and the factors on the left side don't have a 5. So it is impossible for this equation to be true. There's no n or no q that will make this equation true. Therefore, exact equality is impossible. Okay, now let's apply that knowledge. First, let's mention that doubles are a binary floating point representation. For binary floating point, all finite values are represented as the product of an integer and an integer power of 2. So the real-world value v equals some integer n times 2 to the integer exponent e. Now, we'll ask another question. Does there exist an exact binary floating point representation of the value 0.05? So let's formulate the equality. So 0.05 is the same as 5 over 10, and we can, as we did in the previous page, we can reduce that to 1 over 5 times 2 to the 2. And we can see that the exponent e has to be negative because 0.05 is less than 1. That's the only way this equation could be satisfied. And so let's substitute e by minus q. And then if we manipulate the equations, this rational equation, into an integer equation, we get the integer to the integer q will equal 5 times some additional integer terms. Again, these integers cannot be equal if the factors are not equal. And there's obviously no 5 factor on the left-hand side, but there is one on the right side. So equality is impossible. Hence, we can conclude there is no exact representation of 0.05 in any binary floating point format. Not doubles, not singles, not half, not quad precision, or any other binary floating point representation you could think of. As an aside, there is a standard for decimal floating point that would be able to exactly represent this 0.05. However, that is not widely supported. There are some IBM mainframes that support this type, but other than that, there's not a lot of hardware supporting it, and there's not a lot of software that supports it either. So it's not something you could widely make use of. What's really dominant in the world is binary floating point. And so in those cases, things like 0.05 cannot be represented exactly. Okay, so how common is it that a nice looking decimal value cannot be exactly represented in binary floating point? Well, for decimal fractions, for values that have a decimal fraction, it is extremely common that you cannot exactly represent it in binary floating point. To look at that, let's look at this equation. So this equation, we've set it up so that we can have 1 million nice looking decimal values, basically 6 digits to the right, or any 6 digits to the right of the binary point, which is the same as the integer w, where w can be anything from 1 to 1,000,000, and we divide that by 1,000,000. Okay, now if we factor the denominator, we have 5 to the 6th power times 2 to the 6th power and the denominator. Now let's set that equal to a binary floating point representation. So we have that unknown integer w divided by these factors equal to n over 2 to the q. Now, this equation can only be solved if w is a multiple of 5 to the 6th. My apologies, there's a mistake here. This should be 5 to the 6th power. Anyway, so only when w is an exact multiple of 5 to the 6th can you satisfy this equation, because we need these 5's to cancel out. The 5 to the 6th on the top and the 5 to the 6th on the bottom. And so there are only 64 values, multiples of 5 to the 6th between 1 and 1,000,000. So out of 1,000,000 nice looking decimal fractions, we only have 64 of them that have an exact binary floating point representation. So it's a very small percentage of these nice looking decimal fractions that can be perfectly represented. So it's really common to have this imprecision. Okay, so now let's turn that into some math. So we're looking at this equation here and asking, does 0.15 equal 0 plus 0.05 plus 0.05 plus 0.05? Well, the ideal math we all grew up with in school, this would definitely be true. But as mentioned before, your computer is doing something different, and it's probably doing double precision math, at least on your workstation and your personal computer. And in that world, this equation will not be true. Okay? So you want to be aware that this imperfection or imprecision is extremely likely, and you want to make your designs robust to this fact of imprecision being common. Just as an aside, if you're kind of new to this whole floating point, double precision, single precision stuff. What I'm saying might get you nervous that, ooh, this is a bad type and there's a lot of problems with it. It's not the case. As I mentioned in the beginning, doubles can represent values to a precision better than 1 part in 9,000 trillion. It's a huge amount of accuracy. As a result, doubles can represent two values that are very, very, very close to 0.05. To know how far apart these values are, we can get what's called the epsilon of 0.5, which is this value 6 times 10 to the minus 18, a tiny, tiny value. And when a good program parses this 0.5 and maps it to it will map it to the nearest representable double, and it will be no further away than half of this epsilon. So half of this tiny value. So what's going to happen, a program like MATLAB will parse this value and map it to this double value. And so you can see this last part is the error. This last little part is the error, which is 2 to the e minus 18, which is less than half of this value, which again is less than 1 part in 9,000 trillion. So it's super precise, but it's not exactly precise. It's not perfectly precise. Just be aware of that fact, but don't get overly worried about it being imprecise. Yeah, I know that sounds confusing. Anyway, hopefully this example will clarify. So here's an example of a bad design that is thinking that floating point is perfectly precise for all these common values you're going to use. It's like thinking that ideal math, that 0.15 is equal to 3 times 0.05. Ideal world, it's true. In double math, it's not true. So in this program, we have a loop that has a termination condition that depends on or a continuation condition that depends on an exact inequality. So if these values are not equal, keep going, keep going, keep going. And so what's happening here is the accumulator starts out at 0, and the stop condition is, the stop is 0.5. It's actually the nearest double representation of 0.15. Okay? And then this accumulator starts at 0, and each time through the loop we add delta to it, which is the nearest double representation of 0.05. It's not ideal 0.05, it's the nearest representation of 0.05. So we come through and we add that slightly imperfect value to here, and we keep adding, and we were naively, the way this was written, I was naively expecting this to stop on the 4th time through. But what happens is, we added, we added, we added, we got to the point where naively we would have thought the two sides were equal, and this condition would have caused us to stop. But it didn't, it kept going. And basically we would have had an infinite loop, except there's a little extra protection code that I threw in to avoid the infinite loop. Okay? All right. So if we look more closely and try to debug what's going on, we can basically do a printout where we're printing out the double precision values to 18 digits of accuracy. That will make sure that we can always distinguish two double values that look close at a few number of digits, but are actually different. So here, as we're going through the loop, we see that the 0.15 actually was parsed and mapped to this nearest double value. 0.005 was parsed and mapped to this double value, which is a little bit bigger than the ideal, and this one's a little smaller than the ideal. And so we add this value, and we get here, and we get here, and now when we've added 3 times, this value is a little bigger than what this value was. So they're not exactly equal, and the loop keeps going. And again, this extra runaway stuff prevented it from keep going, but that's not the point. We wouldn't. Our goal is not to have to deal with that sort of stuff. So anyway, you can see here that this equation we asked about before equals this value, which does not equal this value, and hence the loop just keeps going, which is not a good thing. All right. So a better design uses tolerances and uses range checks rather than exact equality checks. Okay, so in this code, we've got the same delta, we've got the same stop condition. Well, not exactly the same stop condition. We've modified the stop condition to have a little bit of tolerance on it. Okay, we said this should be, each time we should be going up in increments of a full delta, but we've added a little extra 1% headroom to make sure that if it's off by a few epsilon, we don't accidentally stop a little bit too early. Okay, so the tolerance, we can control the tolerance to stop, to give a little extra or give a little less. You need to think about that and just that as what's right for your problem. Should it go through the loop 3 times or 4 times? All right. Now the really, really, really important change here is we're not using an exact inequality. We're using a range condition. So if the accumulator is less than or equal to this stop with tolerance, we keep going. But once it's above, anywhere above, it will stop. So we'll avoid that runaway infinite loop. And so now in this case, with using the range condition and using the tolerance, this behaves as expected. We go through the loop 4 times, and everything is good. So again, biggest, most important thing is use a range relationship, not an exact equality or inequality. You also may need to think about adding a little tolerance to get what you want, given the fact that you can have imperfections in the parsing, and those little errors can build up as you're doing mathematics. Now, some of that pain of having to think about this little tolerance and delta, there are many conditions where you might be able to just avoid that by setting the problem up in a different way such that your loop counting is controlled by an integer. Your integer goes from 0 to 3 and then you stop. And if you wanted to know what the floating point value that was related to that integer, you could do a simple equation by like taking the integer and multiplying it by delta. The advantage there is that you don't have those imprecisions building up each time you're doing an addition. It's all controlled to just that one simple equation. Okay, so in summary, doubles are an amazing, super successful data type, but they are not perfectly precise for all values. In fact, the vast majority of nice-looking values with decimal fractions cannot be exactly represented in binary floating point. This includes doubles, singles, quad, half, and so on. So better designs are aware of and robust to this common imprecisions that you will face with double or single or whatever. And the designs avoid pitfalls like exact equality tests. They use tolerances and range tests like less than or equal to properly control conditionals based on floating point values. Or even better, look at restructuring your problem so that you can do counting actions like loops or absolute time accumulation or angle accumulation using integer or fixed point. These have a nice factor of having controlled precision, which can often be used to good effect. Okay, that completes this presentation. Thank you for your attention.